Welcome to our webinar today. The topic of our webinar is network slicing in 5G. We're going to be going for an hour here today. So I'm actually in the US on Central Time, so we're starting at 11 a.m. Central, and we'll be finishing at noon Central Time in the US. My name's Paul Shepard. You can see my email address there, and after this webinar, please feel free to contact me if you have any questions. We are recording this session, and that recording will be made available to you sometime this week. I am going to get started, and the first thing I'd like to do is to introduce Award Solutions. We have partnered with some of the best network operators throughout the globe to partner on teaching technologies that for wireless networks, not limited to just wireless networks, but also other enabling technologies such as networking, network function virtualization, and automation and artificial intelligence. If you're unfamiliar with us, please feel free to visit our website at awardsolutions.com. And also, I'd like you to know that we are also a technology training partner to Mobile World Congress and participate in the MWC events, as well as other industry events as well. This is me. I've spent many years in the telecommunications industry at Award Solutions, where I've been here about 8 years. And my focus has been on instructing and developing courses in the area of 5G core, most recently, VoLTE and IMS, LTE, and network function virtualization as well. At Award Solutions, we offer many, many different styles of training. So instructor-led training, either in person or remotely over the web, as we're doing here today. E-learning, which is very much self-paced, run at your own level. Blended learning, which is a combination of both instructor-led sessions and self-paced learning. We offer videos on various topics. We have podcasts, and we also do webinars such as this one. And we have a number of webinars that we've started doing this year and will continue into next year as well. This is a web-based training session. So I would ask, please, if you haven't already done so, to please mute your microphones or speakers or whatever, so we can keep the background noise to a minimum. I do encourage you to ask questions. I will allow time for questions at the very end, but if anything comes up in the meantime, please feel free to use the chat window to ask any questions. Please do not take any copies by any means of the material. This material is the intellectual property of Award Solutions, and please place your phones on silent mode if you have them active. Thank you very much for cooperating with that. We often provide special promotions for some of our training, and this is an example here. We have a course that is running two times in January, one for Europe, Middle East, and so forth, and one in North America. The topic is 5G networks and services, and this is a kind of high-level to medium-level introduction to 5G. It is a 2-day class that is either run as 2 complete days or as 4 half days during a week. Right now, there is a special. If you sign up and register for this class before the end of the year, there is 40% off. And let me just take the opportunity to drop this link into the chat window for you, in case you would like to go access that. Also, you can also scan the QR code that's on the screen as well. Okay, so that link is in the chat window. 40% off if you sign up before the end of December. And I'll give you a reminder of this a little later as well. And if anyone has any questions about that, please feel free to ask me. Okay, let's get to the subject matter for the day. So network slicing in 5G. We'll talk about the motivations for network slicing. You know, why are we doing it? What's the objective? What does it do? What does it help with? And then we'll explain how a 5G network can help deliver network slicing. We'll talk about what the types of services are for network slicing. And we'll also describe how a 5G device accesses a specific network slice or one or more network slices and how that procedure works. We have basically two topics that we'll go through in this hour. First of all, we'll talk about what's the motivation for network slicing in 5G. Then we'll talk about some ways in which network slicing is implemented and what it means. And finally, at the end of the session today, we'll have some time for some questions and a little bit of a wrap-up. So why do network slicing? I'd like you to think for a moment about the existing wireless networks that we have today. 4G LTE. 4G LTE, it's a fantastic network. It's provided us with much higher data rates than we're typically used to with sort of second and third generation wireless networks. It's an all IP network. It is great for doing things like accessing the internet and web browsing and streaming videos, doing all of the social media services we do on the internet, email, and so on and so forth. And also for doing voice in the form of VoLTE, packetized voice, packet service voice. But in LTE, it's a little bit of a one-size-fits-all scenario. We can differentiate traffic in LTE. We can differentiate traffic through quality of service and by prioritizing some traffic over another. But when it comes right down to it, every user who's connected in a cell on LTE and connected through the core and the transport, all those users are all using the same resources. It's a shared resource. The network is shared. And not only that, but all those users are in contention for all those resources. So LTE is a bit of a one-size-fits-all. Users are all in contention for the same resources, and the network is really optimized for internet-type browsing, basic broadband-type data activities. Now, in 5G, that picture is going to change a lot. 5G has the promise of introducing an awful lot of new, diverse services. These services could be the connection of many, many different types of IoT type devices, Internet of Things, smart home, smart cities, autonomous cars, sensors in cars, sensors in all over the place for oil wells or electricity meters, smart wearables. All of these things are going to be new types of services that 5G will help support. Secondly, with 5G, we'll also be able to have a lot more and more varied business type models, right? Business versus consumer, third-party services, the communication or operator provided type services. So as we start to get into this new range of services in 5G, what we find is that a one-size-fits-all network really isn't the right thing, right? We can't have contention for all the resources amongst all the users of these new types of services and applications. And secondly, there's going to be a need to optimize the network differently to meet the very diverse performance requirements of these different applications. So the solution to that is network slicing. Network slicing is all about taking that one physical network end to end and dicing it up into virtual slices, with each slice being able to be managed independently, with each slice maybe having dedicated resources that are not used in other slices. And therefore, we can now optimize those slices to meet these very, very diverse performance requirements that are going to come in 5G. Now, 5G itself has a set of targets. These targets were laid down by the ITU during the very early days before 5G specifications were developed. Those targets include being able to provide to the users up to 20 gigabits per second, downlink data rates, and up to 10 gigabits per second uplink data rates. So you can see right away that those performance targets are way exceed what is available from LTE today. Latency. Some of the new applications and services that we will be doing in 5G are going to require very low latency to be effective. Less than a millisecond on the air interface, for example. Connection density. The more and more we get into the Internet of Things and a multitude of different types of devices accessing the wireless network, we're going to need to be able to support an extremely high number of connected devices in a specific area. And the target for 5G is up to 1 million devices per square kilometer. Throughput, 10 megabits per second per meter squared, a measure of the spectral efficiency. Cell edge data rates, downlink, 100 megabits per second, which in itself exceeds 4G LTE capabilities, and uplink 50 megabits per second at the cell edge. Now, what do all these performance requirements for 5G mean in terms of network slicing, and how do those tie into specific applications and services? So we're going to look at 3 usage scenarios. These usage scenarios were developed by the ITU and have subsequently been adopted by 3GPP as 3 standardized network slices. Now, each of these usage scenarios has very, very different, varying types of performance requirements. The first one is called eMBB, or Enhanced Mobile Broadband. eMBB is intended to be able to provide the types of services that we typically use 4G for. Web browsing, video streaming, the type of traffic, email applications, the type of traffic that often requires very high peak data rates, maybe is not too sensitive to latency, is very bursty in nature. So being able to provide that type of support those types of services is what eMBB is all about. And eMBB is one of the standardized network slices. The second category of slicing is called ultra reliable and low latency communications, or URLLC. A certain class of applications, an example, self-driving cars, virtual reality, augmented reality, have very, very strict round-trip delay times in order for them to operate effectively. Some of those applications also need a high degree of reliability. Mission-critical type applications, applications to do with healthcare. So UR LLC is the second usage scenario defined by 5G. And the third one is called MMTC, or Massive Machine Type Communications. And in this usage scenario, we're looking at a category of services where we need to connect a huge number of devices, for example, the Internet of Things, a huge number of devices in a given area, but those devices may not necessarily need extremely high data rates or extremely low latency. They may be fairly short, bursty, low bandwidth type devices that do not have specific characteristics of a lot of them, but not necessarily high data rates. Smart cities, smart home, wearables are all example of those. Now, in this pyramid here, this pyramid is really all about saying that, well, no one specific service or application can necessarily fit precisely at one of the points of this pyramid, right? They probably sit in between. So as we go up this side of the pyramid, we're really talking about increasing data rates. And down that side would be increasing connection density, for example. And again, this would be increasing data rates. And then going down this way would be increasing or reduced latency. So now you can see that certain service types fit somewhere within this pyramid. 3D and ultra high definition video obviously requires extremely high data rates, but latency for one-way broadcast is not really that big of a deal. Controlling jitter is, but end-to-end latency isn't. But when we get into augmented reality, virtual reality, not only do those applications require a lot of bandwidth, but they also have very strict latency requirements as well, and so on and so forth. So those are the three usage scenarios defined by 3GPP. Now, in network slicing, as we'll see later, we are not limited to just these three standardized slices. We can have others as well. But as you start to get into looking at network slicing, you're going to come across a term called the SST. It is the Slice Service Type. And this is just simply a number that has been assigned by the standards for these standardized slices. And EMBB is SST1, Slice Service Type 1. URLLC is SST2. And MMTC is SST3. So at some point you may run across those SST values in your jobs. So network slicing is all about providing suitable end-to-end quality of service and optimize resource sharing, or maybe even dedicated resources. We've talked about the three standardized slices for mobile broadband, low latency, and massive IoT type services. Now, one of the very important characteristics about network slicing, it is an end-to-end capability in the network. From the device, through the air interface, through the G-Node B, through the backhaul and transport networks, through the core network, and to the management systems. It's an end-to-end capability. So what that means is, for us to be able to do network slicing in 5G, we need both 5G RAN and 5G core, i.e. an option 2 deployment scenario. 5G RAN, 5G core, 5G network end to end. So in order to put a slice in place in the network, we will slice the RAN, slice the transport, slice the core, slice the management systems as well. So as you can see on the graphic here, network slicing is, rather than just having slices of one fruit, an apple, network slicing is slices of multiple fruits, each with their own characteristics, their own flavor. All right, at Award Solutions, we like to use these terms called define in 9, a 9-word definition. So the definition for network slicing is it's a service-based logical network on common shared hardware. Now, providing services and applications to meet specific service types is not a new concept. It's not new to 5G, right? Some of this has been done in 4G, for example, corporate VPNs or MVNOs. But the problem with those types of solutions is they are not end-to-end solutions. Even though you may dedicate gateways like a PGW in LTE to a corporate VPN, all of the other resources are still being shared. So network slicing in 5G is fundamentally very different from those types of solutions. And if anyone has any questions, I'll pause here briefly. Okay, so let's go on to look at what this means in the 5G network. So first of all, in terms of devices, and remember, now we're talking devices in 5G. We're not just talking about traditional consumer smartphones, but the types of devices that, for example, may be in cars, V2X, vehicle-to-vehicle type communications, or the type of slices for IoT type devices, Internet of Things, smart wearables, transceivers, meters, point of sale machines, and so on and so forth. So those could be examples of different service types for which an operator may want to provide network slicing. Raj, I was not planning to talk about AI in the role of network slicing, but I could certainly just talk a little bit about what the impact may be there as well, a little later. So in order to provide this service, we are going to dice up the network, a RAN slice, a core slice, a management slice for these different types of services. And when we dice up the network, we may or may not allocate dedicated resources. For example, the UPF, the user plane function in the 5G network, that is the gateway, the only gateway in the 5G core that transports user traffic between the G node B and external services. It might make sense to dedicate UPFs or a number of UPFs just to one type of slice, so that we can then optimize the performance of those to meet the specific service requirements. So what are some of the capabilities in 5G that help enable network slicing? So first, at the very top, 5G provides us with a much wider array of spectrum that is available, going all the way from low band, high penetration, high propagation distance type cellular services at 600, 700 megahertz, all the way up to millimeter wave radio that has very different characteristics, smaller propagation distances, but can support very high data rates, can support massive MIMO, massive beamforming. So being able to take advantage of those different pieces of spectrum is one of the enablers for network slicing. User subscription data. In LTE, we provided in the subscription data a list of PDNs or APNs, access point names, that a subscriber could access. In 5G, the terminology that's used for that is called a data network or data network name, a DNN. Now, what happens in 5G is we allocate for a subscriber a specific data network to a network slice type. So when the user wishes to connect to that service, they are going to be assigned to a specific slice type. Software-defined networking, separation of control plane and user plane, very important concepts. By separating control and user plane network functions, and remember the UPF is the only network function in the user plane, we can scale those things independently to meet our requirements. NFV. The 5G core will be implemented as virtualized network functions running on an operator's cloud computing platform. If we're virtualizing those network functions, it makes it a lot easier to scale, gives us a lot of flexibility in deployment, again, to help support network slicing. Network slicing does not have to be static. It can be dynamic. And what I mean by that is at any point, based upon time of day or day of week, or based upon traffic patterns, we can adjust the amount of resources allocated to a specific slice. For example, we may want to allocate more resources to EMBB during the evening if people are streaming videos or doing broadcast TV over the wireless network. However, we may want to allocate more resources to vehicle-to-vehicle communications during rush hour times of day and so forth. So dynamic allocation and reallocation of resources is a part of network slicing. It does not have to be static. The 5G core. The 5G core is a significant advancement over 4G LTE in terms of the number of network functions and the way those network functions will be implemented as virtualized network functions, allowing for a lot of flexibility and scalability to help support network slicing. In addition, in 5G, unlike LTE, there is a lot more flexibility in how network functions can be allocated to subscribers. There are less restrictions. For example, a subscriber may be served by many UPFs or many SMFs if they're accessing multiple slices and so forth. So what are the building blocks in terms of the network capabilities in 5G? So on the air interface, there are certain characteristics of the 5G NR or new radio that really help with network slicing. First of all, we have extremely large bandwidth available. We mentioned that the target downlink data rate is 20 gigabits per second. That can be achieved because we can have a lot more spectrum deployed in 5G from low band to mid band to high band, and those channel bandwidths are a lot larger too, up to 400 megahertz. Now, if you're at all familiar with the air interface in LTE, you will know that the data rates I can achieve on the air interface are directly proportional to the width of the channel. LTE started at 20 megahertz max and then expanded through carrier aggregation up to 100 megahertz. Now we're talking about 400 megahertz channel bandwidth. So that can provide a lot higher data rates, and also the millimeter wave radio, the higher frequencies help with higher data rates as well. beamforming and MIMO, especially when we get to millimeter wave radio. Millimeter wave means very small wavelength, very high frequency. In wireless networking, or in wireless in general, the antenna size is a function of the wavelength. The smaller the wavelength, the smaller the antenna. In macrocellular type networks today, we are used to seeing those poles with bigger tall antennas on top of them, 6, 8 foot high or something. When we get into millimeter wave radio, because the wavelength is only a few millimeters, those antenna sizes become very small. So that means we can put together a lot of antennas in a particular radome into what is called an antenna array. And the more antennas, the more we can make use of multiple antenna techniques such as beamforming and MIMO, multiple input, multiple output. Massive beamforming, massive MIMO, that implies that we can reuse frequencies in adjacent beams, again contributing to much higher bandwidth. Also in the 5G new radio, we have a very flexible frame structure. It is not fixed like in LTE. So what is called the slot timing is variable. It can be as high as a millisecond or as low as a quarter millisecond. And that quarter millisecond slot timing, which is the time transmission interval, is one of the capabilities that enable for low latency applications. The smaller that slot timing, the more frequently we are sending data over the air and hence lower latency. The split architecture. 5G has been split into what is called a distributed unit that's likely to be at or near the cell site. It implements the lower layers of the air interface protocol stack, those that are very timing sensitive. And the other component is the G Node B CU or central unit. The central unit implements the upper layers of the protocol stack. This split architecture means that we can now put CUs, central units, in common hub or MITSO locations supporting multiple DUs. The CUs can then be implemented using virtualization on cloud platforms, again providing flexibility and scalability. On the 5G core itself, I've already said the 5G core will be virtualized, running on cloud platform. Again, flexibility and scalability. Another capability of 5G is support for edge computing. That is to be able to move processing nearer to the network edge. One of the advantages of that is we can reduce the overall latency. Now, network slicing and MEC, mobile enhanced edge computing, multiple access edge computing, multi-access edge computing are two separate capabilities, but they also have a relationship, because I may wish to put my MEC applications in a dedicated network slice to meet the performance requirements. Now, from a subscriber perspective, there are two aspects that we need to talk about in terms of how subscribers get allocated to specific network slices. But first of all, let's deal with a little bit of terminology. 3GPP has defined this term called NSSAI. It is the Network Slice Selection Assistance Information. Now, that is an extremely long-winded term. What does it really mean? It means the slice identity. So NSSAI is that assistance information. It is used by the UE, various components in the network, to help set up subscriber sessions. The NSSAI is a single network slice identifier. A DNN in 5G is a data network name, equivalent to an APN in LTE. A SST is the slice service type. Remember, the standardized ones have the values 1, 2, 3, as I mentioned earlier. And an SD is a slice differentiator. And we'll come back to that one in a minute. Now, in the device itself, we may or may not provision, this is optional, network slicing information. If we do put that information in there, then basically what it is a list of slices this subscriber is allowed to use and the data networks that will be allocated to those slices. This slice information is also in the subscription profile. In 5G, our subscription profile is held in the Unified Data Manager, or UDM. The UDM is going to have a list of all the slices this particular subscriber can use, and within each slice, the particular data networks that subscriber can access. For example, we would say SST1, which is EMBB, and in this slice, this subscriber can access the data network called the Internet, or the data network IMS, and maybe some others as well. And depending on the subscriber, and depending upon the types of devices, they may be allocated to different data networks to different slices. The point is here that it is predetermined where a data network is going to be within a network slice. So this would be this type of subscription information we would expect for typical retail subscribers with smartphones, you and I. Now, the AMF in 5G is the access and mobility management function. It performs a lot of the same functions as the MME used to in LTE. So it's responsible for UE registration. It's responsible for mobility tracking. Doesn't do session management. That's the function of the SMF. When we power up the phone, we go through a registration procedure in 5G. That registration procedure will include selecting and allocating an AMF. Now, like all network functions in 5G, not all network functions, specific instances, need to serve all slices. An AMF, for example, may be allocated just for EMBB, for, say, retail type subscribers with smartphones. If a particular device needs to connect to the network and needs access to more than one slice, then we may have to pull in another AMF to help serve that particular subscriber. The AMF will select the slice information provided by the UE if it's available. During the registration procedure, it will get all of the slicing information for that subscriber from the UDM, and it will provide that information back to the UE during the registration accept message as a list of allowed network slices. So one of the key messages from this particular slide is, do not think of slices as being something a subscriber requests. That allocation of data networks to slices is predetermined in the subscription information. The subscriber is totally unaware of network slices. Okay, so the subscription information has the list of network slices, and the SST and SD identify the slice type and the slice differentiator. So again, just to take that particular thought a little bit deeper, during registration, the device will send a NAS register request that will be carried towards the G-Node B, and also an RRC connection setup complete. The G-Node B will know the slice information provided by the UE. It will select an AMF based upon that slice information. If the slice information is not available, then that AMF can be changed later. In 5G, we set up 3 connections between the RAN and the core. N1, which is for NAS messages, N2, which is for G-Node B to AMF signaling, and N3 for user plane traffic through the UPF. In the 5G core, AMF may serve 1 or multiple slices. UPFs can be allocated and dedicated to network slices, or they can be shared. The UPF is responsible for taking all that user traffic and switching it between, or routing it between G-Node B and external services, and enforcing quality of service. SMF is a session management function. The NRF, the network repository function in 5G, is used by all other network functions to facilitate selection of network functions. The NRF, when network functions register in the NRF, they will register based upon the specific slices that they support. NSSF is used by the AMF to select an alternate AMF if we need to, due to slice support. PCF is a policy control function. So all the network functions in the 5G core can serve 1 or more slices. They can be dedicated, they can be shared. And there could be multiple of them. All right, so what are, again, some kind of types of slices? Here we show a number of different types of devices. The smart car, autonomous car, would access the automotive slice. The automotive slice may provide services like some advanced traffic navigation guidance type systems, or whatever it might be. Utility meters. We'll put in an electric utility slice. Lots of them, pretty low data rates, pretty infrequent data transmission. So we can support a lot of them. Don't need a lot of resources. We only give them a little bit of resources. Consumer slice, for example, for broadband type services, those types of things. Now, the 3 standardized slices defined by 3GPP, I gave you the SST values earlier, 1, 2, and 3. Now, for those 3 standardized slices, they do not have a slice differentiator. Those 3 standardized slices mean that we can support roaming between operator networks because those slices are standardized. An operator may define their own slices. These would be unique to a specific operator, and we would not be able to roam using those non-standard slices. An example, we may provide an enterprise VPN and call it SST99, and the slice differentiator could be a customer identity. A slice differentiator simply means an instance of another instance of that slice. So enterprise VPN may be multiple slices with the same SST, but different SD, slice differentiator values. Train company IoT, SST98, smart streetlights, 97, and so on and so forth. There is no limit to how many slices an operator can define. The anticipation and expectation would be that as we move forward, operator may choose to serve specific vertical industries with network slices. Okay, I mentioned earlier that network slicing is end-to-end. So whenever we put a slice in place, there's going to be a slice of the RAN, a slice of the transport, a slice of the core, and each slice can be managed independently. If I allocate a number of network functions and a piece of the RAN and the transport to specific slices, then I can manage independently within those, right? I can manage the resources, I can optimize the resource to meet varying diverse performance requirements. So here we're showing, for an example, network slice for MBB or eMBB, V2X, and IoT. Each of these is like an independent virtual network. All right, so how do I achieve slicing in these different areas? So in the RAN, a mechanism to split up the RAN is to split it by channels. For example, I may allocate a 100 megahertz channel, right? Let's say in 600 megahertz spectrum, or somewhere in low band up to, 2.4 gigahertz, typical PCS type spectrum. I may put a 100 megahertz channel slot in for MBB type services. V2X, I may decide to put in a 50 megahertz channel at one of the frequency ranges, supporting mini slot meaning smaller slot timing. IoT type devices, maybe not need a lot of bandwidth, but I need a lot of connectivity. Let me put in a 20 megahertz channel, maybe at different frequency ranges, and so forth. So that's how we could slice up the RAN, allocate different parts of the spectrum to different network slices. And this could be mid-band, this could be 3.9 gigahertz, for example, if that spectrum was available. Or it could be a piece of the 700 megahertz. So that's how we slice the RAN. In the core, because our core network is implemented on a cloud computing platform, we may have core network functions at an edge data center. We may have them in a local data center serving an entire market region or a state, or in centralized data centers, right? 5G provides that flexibility. And we have both control plane functions and user plane functions, and we could allocate different instances of those network functions on the edge computing platforms, on the cloud computing platforms to specific network slices. So for example, video on demand, content server cache. And we can change this allocation dynamically if we need to. In the transport network, the use of SDN, software-defined networking, which separates out the brains or control aspects of IP routing from the physical packet forwarding functions, again, enable us to set up specific paths, traffic paths or routes using specific IP routers in the transport network and allocate those to specific slices. Management and orchestration is, over the last few years, has become a huge topic. Being able to provide management models based upon, for example, ETSI models that are consistent, so that we can have some consistency about how we manage the network and are not as much tied into vendor-specific solutions. So Mano models also fit into network slicing, where at the very highest layer, I may have a service instance layer, service management functions. For example, company X comes in and says, I'd like my own VPN and my own slice, for which presumably they'd pay some money. We can go define those characteristics at the service instance layer, pass that down into the network slice instance layer to say, these are the resources I'm going to put in place and allocate to that slice. And then down at the physical resource, actually instantiate and manage those resources for that slice. In the entire network slice lifecycle management model, NFVO, managing the slices, the virtualized infrastructure manager for the cloud computing platform, virtualized network function managers, element management systems can all fit into that and can all be allocated specifically to different network slices. So the goal here is to be able to operate each slice as if it's an independent network. Manage it accordingly, optimize its performance. So what might be some examples of network slicing use cases? Well, we've talked about the 3GPP standardized slices, EMBB, URLLC, MMTC. What about service levels, right? Bronze, silver, gold. Give different service levels, say, to consumers, not just for their smartphones, but maybe for fixed wireless access as well, right? Broadband over wireless. Different data rates, maybe different levels of guaranteed latency, and so forth. Different service types, Internet of Things versus vehicle to X. Logical networks for MVNOs, right? MVNO operators are supported in existing networks, but they're still sharing all the resources. Well, now I could allocate a slice of the network to an MVNO and say, this is all yours, and you can manage within that. Business versus consumer slices, accessing corporate networks versus typical consumer type services and applications that we use on our smartphone. And finally, different market segments, healthcare, utilities, factory automation, whatever it might be, right? Each of those may have specific QoS requirements, and we can optimize a slice of the network to meet those requirements. Factory automation, for example, probably means a lot of devices, probably requires very low latency in order for that to operate successfully. And we could tie into this the implementation of a set of small cells within a company, within a factory. So those cells, maybe operating at millimeter wave, would only be usable by devices within that factory, thus providing that factory with its own set of air interface resources that would not be interfered with from the macro cellular network. Okay, I have another question here from Raj. Will it be touching on OANM? Not other than I just talked about, Raj, on that high-level slide about MANO and so forth. Was there a specific question you had? All right, let me know if there's something specific. Let me get back to Raj's question on AI. So network slicing doesn't require AI, but AI could be very useful for network slicing. For example, we talked about being able to dynamically allocate and reallocate resources between different slices based upon, say, traffic demand or time of day or something. Well, I can see where AI systems could come into use for that in terms of being able to predict, for example, traffic spikes or changes in traffic demand based upon existing models and historical data. Therefore, that would enable us to put models in place, AI models, that could automatically and dynamically adjust the resources for the various slices based upon that data. So I think that's one example of the use of AI. Does that help, Raj? Okay, any other questions from anybody? In fact, let me open this up for a general Q&A time. If you have any questions, please let me know. You can speak them out or put them in the chat window. All right, Is it inevitable? You know, I bet if you asked 100 people, you'd probably get 100 different answers. I think it is. And I think it's inevitable because I know operators are taking it seriously. So I think AI is inevitable in the telecom industry. In terms of the presentation, you will get a copy, or you'll get instructions on how to get a copy later on after this class. So that will be made available. Okay, couple more things from me. We got just a couple of minutes left here in the session. I'd just like to put up our 5G curriculum. We have a lot of training in 5G, and it goes all the way, you know, at the top level here, some foundational type courses. A lot of these could be anywhere from an hour-long self-paced to sort of up to 1 day, or a lot of half-day classes in this area as well, 4-hour sessions. And then we have more advanced type classes that typically are multi-day, going into things like the air interface, network and services. We have various blended learning classes for the RAN and also the core side. And these cover the access, optimization, and the core network. Those are kind of the 3 categories. The light blue is self-paced e-learning. The orange is technology primers. Those are half-day, 4-hour sessions. The green ones are in-depth, multi-day classes, and the gray ones are blended learning. If you'd like more information, please go to our website. I encourage you to go to our website anyway, because you will find there are a lot of resources about 5G there, and LTE as well. So I'm going to put our website in the chat window. Right here. If you go to our website, you'll find lots of papers and blogs about 5G, some videos. We also have a lot of stuff that's been published on LinkedIn, and we have a YouTube channel as well. So check those out at the same time. And please feel free to contact us. info@Award Solutions will get there, or through the website. And one final reminder on the free offer, question from Jennifer. Where do you see the greatest need to focus on the business side of IoT to build the use cases to leverage 5G technical capabilities? Yeah, I think you've answered your own question, Jennifer. You have to build the use cases. I think that's the thing, in the business case, because you know, a lot of telemetry type devices use wireless communications today. Point of sale devices in stores use a lot of old 2G, 3G type technology, or even dial-up in many cases. So I think building the business case around, you know, how would you replace those, and what would be the advantage of deploying them as using 5G wireless versus the older technologies, does require a very solid business case. Think about all those millions and millions of point of sale type devices out there that, you know, swipe your credit card. My email ID, I did have it at the front, but let me put it in the chat window. Did I spell that right? I think so. pshepherd@awardsolutions.com. Okay, we're just about coming to the top of the hour. Any other quick questions? Please take advantage of our special offer. Please visit our website. There are places there for you to get information, ask questions, talk to our experts, and so on and so forth, watch videos, etc. It is right at the top of the hour by my clock. So thank you very much for your attendance today. and look forward to maybe seeing some of you in another training session with Award Solutions at some time. Thank you very much, everybody, and have a good rest of the day.